And does it look like we're recording?
Yes.
Okay, great. So I want to walk you through, first of all, Canvas. How many are brand new to Mesa College this semester? Okay, so this is maybe totally familiar from another school, or maybe you've never done anything like this. But Canvas is wonderful. It's a bulletin board. We used Blackboard for many, many, many years. Canvas is an improvement. Canvas is where I put stuff up so you can go get it. It is not meant for communication. Please never send me an email or any work through Canvas. The most I will get is a notification that somebody tried to contact me through Canvas. I won't know who, and I won't know what. Now, if you have to email me, use the email. And having said that, I have people that will do everything through Canvas and say, you're not getting any of my work. Canvas is a bulletin board for me to communicate with you. It is not made for you to communicate with me. That's what email is for. Now, if an instructor set up their class that way, there's a lot of work to set it up so that you can go through Canvas. It's way more trouble than it's worth. We're meeting live. That would only be for an online course that they would do that. We have no reason to do that. So this is what the home page looks like. Everything in the course is located here under modules. And I've got it neatly organized. You see notes, videos. Now videos are 5 to 15 minute little snippets. When we first went to the online environment, March 11th, 2020, I remember the date very well. That's when the NBA and the NHL postponed their seasons. The next day they said, we're done. And we were not back on campus for a very long time, over a year. We had to immediately go to an online environment. So what I did was I made a lot of short little videos, just using the cell phone and different things. Not long explanations, just short things to help you get through. And most of the students say those are the ones that they find the most valuable. And so every single topic I'll have little short things on. I have Zoom lectures because for a year I had to do everything through Zoom. These are the entire lectures. They're usually a little bit shorter because when you're going through Zoom, you can't have 2 hours. Nobody has that kind of patience. And then there will be the live lectures. Now, the Zoom lectures, the advantage of those are, these are pre-recorded, so if you wanted to look at something ahead of time, you could. Same with the other ones. The live lectures will be posted after class. But if there's one bright spot that came from the pandemic is that you have access to resources that did not exist 3 years ago. There were only 2 professors. I've been here for this is my 37th year here. There's only 2 professors who have ever taught an online class, and it was only online statistics. We never even considered doing anything online. And then all of a sudden, everything had to be online. So I had to write tremendous amounts of notes. I had to do videos. I have over 500 YouTube videos. It's hard to believe. No joke. They used to refer to me. For years and years and years, I was the Chuck Norris of mathematics. Now I've become the Justin Bieber of mathematics, apparently, because I have a YouTube channel that has tens of thousands of hits, and I don't even know who's watching them. It's math videos. You know, who does that? But apparently people do that. And so I don't need you to find anything. I put everything on Canvas for your convenience. Now the thing is, if you wanted to watch other videos, let's say you wanted to watch a Calc 2, integration by parts video or something, when you're watching one of the videos, as you know, it's YouTube. So everything on the right, you'll see similar videos. You can always click on something. You can always find something. If you actually want a video on another subject, use calculus, for example, just ask me. Or you could actually probably just search it, and you could probably find it. But everything we do will be located here on a daily basis. Now, the bottom here, quizzes. Now, the way it's going to work, I'm going to go to the syllabus in a moment. The quizzes are always going to be posted over a week ahead of time. So you have plenty of time to look at things. The first quiz is due in a week, but it will be based on today's lecture, and it's already posted, so hopefully, at the end of today, you could probably attempt it and do just fine on it. Okay? And then the exams, when they happen, and the practice tests will be posted here. You'll know way ahead of time. So let's go to the schedule. Okay, this is really important, this part here. Okay. Now, if you're trying to print something, you want to print the syllabus, you want to print the schedule. You see how I clicked on it and it comes to this screen here. This is not the screen you print from. What you're going to do is right here where it says download, you're going to click the download. Then it's going to show up in that lower left corner. Then you're going to click that. It's a little bit of extra work, but when you click that guy, did anything happen in there? There we go. Now it'll take up the whole screen, and now it's in a version that can easily be printed. Plus you can see it easier. So that's the order of things. Hit the download, and then in the lower left corner. So this is the schedule. I do this in all my classes. This is a detailed, every single lecture, here's exactly what we're going to do. We're never going to deviate from this, not by 5 minutes. I do have the good fortune is I've taught Calc 1, Calc 2, Calc 3, linear algebra, discrete mathematics, differential equations. Each of those courses I've taught more than anybody who works in the district. Each of them, because that's what I teach every semester. So I've taught this course, I don't know, 75 times. I've taught Calc 1 over 100 times. I know exactly how long to spend on each topic. So this is what we're going to do each day. We will not deviate a little bit from this. So you know. Now the reason I also post it by the lecture topic is that you don't all have access to the same textbooks. If this were Calc 1, we'd all be using the same book. That's obvious. But then in Calc 2, is it all the same students? Not necessarily. By the time you get to Calc 3, some of you have had to use 2 different books. Has anyone had to do that already? Change books? It's awful. Calc books are expensive. So the rule is whatever book you have, that's the book you're going to use this semester. Okay? I could care less what Calc book you used. They're all terrible. They're all horribly written. They're all money grabs. But they're the only place you can get your homework questions from. Some people like to use OpenStax. I tried it last semester. OpenStax is free, and you get what you pay for. It is so substandard. The highest compliment I've ever heard was it was adequate for the course. But actually, it's very, very substandard. And for calculus, it's horrible. You won't get 10% of the problems that you need. So whatever textbook you have, and there's so many PDFs online that you can just go anywhere. I recommended Tan or Swakowski because I've used them both, and they're both out of print, which means they are dirt cheap. Did anybody look online for either one of those, by the way? I saw both of them in the $10 range last semester for a 3-semester book that was $300 brand new. That's why I'm saying that those are good sources and great sources for homework questions. So you notice, okay, today is lecture 1, and you see a week from today, over here, you see quiz 1. Quiz 1 is based on today's lecture. I will do problems, I will do explanations, I will derive things, I'll practice stuff. Then you go home, you practice problems in the textbook, you get good at it, and you sit down and take a quiz that's the exact same stuff, just a few questions. Did you understand what we did? The quiz is due at the beginning of class every day. Does anyone here have to drive a ways to get here? Especially 15? Here's what most all students do. They figure it out really quickly. I don't accept late work because if I accept late work, I have to accept all late work. There's no such thing as degrees of late, okay? There's nothing. If you played in a sport and they started the game without you, it doesn't really matter how late you are, the game already started. There's no late work, so if somebody's 10 minutes late, if somebody's 10 hours late, it's still late. I can't take one and not take the other. There's a pretty black and white rule there. So what most people do is, they're getting ready to leave, they take a picture of their quiz, they email it to me, that takes about 10 seconds, and then they come to campus. Why? Because the day you didn't do that was the day there's going to be the traffic accident on the freeway, and you missed class because you're stuck in traffic for 2 hours. That's never happened, right? So what most people do, particularly for an 8 o'clock class, is they just simply send me a picture of their quiz, then they come to class, and then they turn in their quiz. That way, if you're late, or worse, you can't even make it to class, you've turned in the work, and you'll get full credit for it. What you do is, the next time you see me, you hand me a hard copy. I don't like trying to grade emails. It's too much difficult because I can't give you any feedback on the email. So let's say you're absent. Keep it simple. Very few of you will have perfect attendance this semester. So you're absent, but you did the work. You simply email me the quiz. Take a picture. There's something called the Fast Scanner app. Has anyone used that one before? That's the best. There's something similar called Cam Scanner. It's almost identical. It's an app you put on your phone. You can go to YouTube. It's about a 1-minute tutorial on YouTube to tell you how to use it. It's pretty easy. You literally take a picture. If it's more than one page, you go picture, 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 send. That's it. Don't convert it to a PDF. If you do, my computer will recognize it as a virus and I will never receive it. Take pictures. Don't convert it to anything. Just take the pictures and send me the pictures like you would to your friends. If you're out, at the beach and you took a cool wave picture, you don't go home and convert it on your computer and change it. No, you just send the picture. That's all I want you to do. That's your insurance in case you can't be here to turn it in. Now, most of you will find that that's convenient, and most of you will never matter because you're always going to be here on time and you're always going to turn in your work. But that's just to guard against that one day when you might not have been able to make it to class, particularly the day you're sick. Okay? So the quizzes are always due 2 lectures after the fact. So now when you come down here, look at the end of this week here. On 9/14, you see the 2 little slashes right there? That's my way of indicating to you that is the end of the material that will be on that first exam. So if you count, there are 7 lectures, and then you notice what it says exam 1 is 3 classes later because the class before you're turning in quiz 7. Which means before you sit down and take your first exam, you have turned in a quiz on every lecture that you're being tested on. So that way when you sit down and take an exam, there are no questions that you haven't answered already. You've seen everything, you've practiced everything. I also distribute a practice test. I post that online when we finish the material. So on 9/14, there will be the practice test with a key. And so the day before the test, we have lecture, and then we reserve part of that class that says review. That's where we go over the practice test. So any last questions that you may have that weren't answered by you going over the key already. So that when you walk into the test, you've seen me demonstrate problems in class. You practiced them in your homework. You turned in a quiz. You did a practice test. And you got feedback on everything. So there's no mystery when you sit down and take a test. You could write the test for me. You know exactly what is going to be asked on every test. You just don't know what numbers I'm going to use. Okay? There's no mystery. There's no surprise questions or anything like that. But I do reserve the right, every now and then on a quiz, maybe a couple quizzes per exam, I'll throw a bonus question on there. A bonus question will be an over and above challenge from the material that you're being asked. Okay, so there's a problem I really want everybody to try, but it's a little harder than the stuff we've practiced. I might make that a bonus problem. Literally, it's pure extra credit, it's bonus points. So last semester, I taught a summer version of this class, and I do a 6-week Calc 3 every summer for the complete insane people who want to do, math every day. I think we ended with 24 students. We started with 25, we ended with 24, and I think 7 of them had quiz averages of over 100%. People did well on quizzes and they did the bonus problems. How did they do in the class? Well, all of them got an A in class. It makes it a lot easier to get an A when a big chunk of your grade's over 100%. Okay? So, on a daily basis, we will be doing this kind of stuff. So I wanted to go through this. Again, if you're not familiar with Canvas, again, you have an ID number and you have a password. So you have to select your password. Okay, if you haven't gotten on Canvas, please get on today just so you can see how it works. Then if there's any issues, you can ask me. Okay, but Canvas is going to be how I post things so you have them. Okay, and then if you have a question, you can always do that. Now, what if you have a quiz question? Well, I have office hours every day of the week, and for convenience, I have an hour between classes. How many of you are in the linear algebra class later on? Yeah, you don't technically have to leave the room, by the way. You can just take a nap if you want after. There's a lot of people that are in my next class, but I have an hour between classes. That's my office hours. On Tuesday, Thursday, I have a 3-hour morning class, and then I have an hour and a half of office hours. Unless you're on campus Tuesday, Thursday, I say don't make a separate trip to campus. You can, but for a lot of people, that's really inconvenient. It's far more convenient for you to just hang out after class and ask questions because you're already here. And I'm not going anywhere. Now, I do go down to my office, but I usually take my time. If 5 people after class have questions, yeah, I'll answer all of them before I go down there. And then I'm going to come back up before the next class starts. What I actually have to do between classes is convert the video. And that takes a good 30 to 40 minutes. So that's one of the reasons I actually do need to leave so that I can come back and have the next one prepared. Okay? Before we move on, does anyone have a question about the logistics? Yeah.
Yeah, so all your stuff is on PDF via Canvas.
I'm sorry.
Sorry, all your stuff is via PDF on Canvas?
No, I don't convert anything to a PDF.
Or?
It's just posted as a doc, Word
Okay,
docs.
a doc.
Yeah.
So,
by the way, in case you wonder, it takes time and space on my computer, and it is actually much harder to open up, strangely enough. There's only a couple things that I do PDFs for. I'm glad you asked that question, and I do this for certain things. When it's formulas that I post in certain classes, some of your computers can't read the equation editor that I've used. I'll give you an example. I teach discrete math. The union and intersection symbols, as simple as they are, if you don't have a fairly recent version of Microsoft, it won't read them. It'll put hieroglyphics in for the symbols. Some of you have experienced that. So things like that, I will save as a PDF just because it's more trouble to resend everybody. But in general, I don't, just because it requires that I save everything twice. They're just Word docs. But keep going.
Yeah, so do you require us to like print out this stuff in order to like turn in the quiz, or if we do it on like a
Oh,
spreadsheet,
great question.
like-
Do you have to print the quiz sheet? No, but the majority of mistakes in every class I teach, the majority of the mistakes come from the people that didn't print the quiz because they simply did the wrong problem. It's unbelievable how often. Half of you will print the quiz and you'll just staple the quiz to your work. The other half won't. And of the half that won't, at least half of those will have at least one problem that they simply copied down incorrect and did a completely different problem. And just because they don't want to waste the paper of printing the quiz. No, the reason you want to print the quiz is so you have the questions right in front of you. Plus, later on when you're preparing for the exam, retaking the quizzes is one of the best ways to prepare. And if you don't have the questions in front of you, it can be inconvenient. I don't need you to print the quiz, but most of you actually do need you to print the quiz, so you have them right there without thinking. You can do it on campus for almost free. Now, I don't know how it works because they've changed the rules. Has anyone printed anything on campus recently? Do you have to get like a little card or something?
Yeah, you have to like make an account and then put money into it. I think it's like 10 cents a page.
Oh, is it still? I thought it went down. Okay, 10 cents for a page. I mean, you know. I'll have people say they can't afford to print the 10 cents as they've got their expensive latte in front of them, you know, every morning. I think it's easier. I have a printer, so that makes it easy for me. Again, I think it's wise just so you have the written copy and you don't make the mistake of miscopying it. I say that and you think I'm laughing. You know, oh, no. No, if you saw how often it happens, you do perfect work just on a different question. So that can be an issue. All right, let me turn this off. Now let's start doing some calculus. Now, the first part of this class, we really don't do any calculus for a while. There's no derivatives or integrals or anything for a little while. Almost the first month is just devoted to vectors and the mastery of vectors in particularly 2 and 3 dimensions. Now, how many have already had linear algebra? Now, 254. I teach 254. I'm actually the Southern California authority on 254. If you look in your textbooks, my name is the first name you see in your textbook. That's not a joke. Linear algebra is something I take very seriously. We approach vectors from a different point of view, from a theoretical point of view and multidimensional. You're not bound by any dimension. So it's a very different point of view. We're doing it from a purely physics point of view. Most of the math in this class is for physics. How many here would consider themselves an engineer or engineering bound? Okay, then this is the most important of the math classes. How many would consider themselves a math person? Then this is probably the least important of all the math classes you'll ever have, believe it or not. Having said, you never use calculus again in math outside of statistics. That's the only other place you'll ever use calculus again the rest of your life. If you study math forever, what you use the rest of your life is discrete math and linear algebra as the foundation for all of your other classes, because they're all abstract, proof-oriented, except for statistics, which is calculus-based. But for the physics, this is the most important class because it's the calculus in 3 dimensions. Now, people say, what is calculus in 3D? Well, let me go past the vectors for a moment and talk about the calculus part. In calculus 1 and 2, you mastered the calculus of 2 dimensions. That was the whole point. Pre-calculus was geometry, algebra, trigonometry. You got really good at that, and then you did the calculus. And then in Calc 2, you did all the crazy weird stuff, right? Sequences and series, methods of integration. You got really good. So what I want everyone to do is close one eye. Just close one eye for a second. Now, this is what you've done your entire life. You've done this math here. Now, open your eye. What do you notice? Something changed. You just went from 2 dimensions to 3. The problem is the world is 3-dimensional, not 2. So all of the math you've ever done was valid. And you'll never use any of that actually to answer questions in real life because you don't live on a TV screen. You're not a cartoon character. Well, okay, some of you might be, but most of you live in 3D, which means you have to now master the calculus of 3 dimensions. This doesn't mean you start over. It means you take everything you did already and you simply extend it, you expand it, you tweak it to allow it. And what you will find is a lot of the things that you found the most difficult in 2 dimensions actually become easier when you remove that restriction. 2 dimensions is a huge restriction. So what we do is we start a lot of things in 2 dimensions just because I can draw pictures of them. And then we say, now let's extend that to 3, and you'll realize, oh, that's not that complicated. Now, going different dimensions is not as complicated as you think. You have worked in higher dimensions already without even realizing it. And you're going to do functions of multiple variables in this class. The difference, the biggest difference you're going to have with Calc 1 and 2 is in Calc 1 and 2 you could draw a picture of everything you did. One of the first things we're going to learn is how to do a space curve. Tip of my finger, I have a little sensor, and I'm moving it around. You can all see my finger. I have the strange ability. I can create shapes in space, and you can all see them. And then the pixie dust will eventually evaporate. So I'm moving through space at the tip of my finger. You can all see what I'm doing. Can I draw that on a board? Yeah, what would it look like? Yeah, I cannot draw 3-dimensional motion on the board, yet that's one of the most important things we're going to learn in the first month. So we have to change how we look at things. Calc 3, the hardest part for most people is the visualization, the spatial reasoning. Calc 1 and 2 is easy because you can actually draw a picture of everything. There are very few things you can draw pictures of. I can draw a picture of a cube, but it's not a cube. It's still a 2-dimensional rendering of my 3-dimensional idea. And that's the problem, is we all want to draw things. You don't have to draw things, but what you have to be able to do is visualize them. You actually have to see them. In Calc 1, graphing concepts are huge. You spent a lot of time doing graphing and graphing concepts. How many graphs are you going to draw the rest of your life, do you think? Probably none. So why did you do it in Calc 1? Because you had to know what things look like. Because if you were trying to find the area, or a volume by rotation, or a surface area, it's not possible if you don't know what it looks like, because you can't set the boundaries. You have no limits of integration. You have to know what it looks like. That's why you practice graphing, figuring out where critical values were and extrema and inflection points, so that you could then answer questions. Well, we do something very similar in 3D, but we don't worry about trying to draw the thing, but we do learn how to visualize certain things, and we know what they look like. And we'll make token attempts at pictures, so we kind of have an idea, okay? So we're going to start off with vectors, and I'm going to start off with the most basic stuff. I'm not going to assume anything. How many have already taken Physics 195? Okay, so you have a lot of exposure and experience with vectors. Believe it or not, that will only help you for a really short time. A lot of people go, oh, Calc 3 is going to be so much easier because I've already done vectors. The problem is, in Physics 195, I find people have some of the worst habits. They worked with vectors, but they did things that are not really valid. You know, they divided by 0, multiplied by infinity, you know, crazy mathematical stuff, and they go, well, I got the right answer. It's like, but nothing is equal. Nothing, you know, crazy stuff, because the physics professor just wants you to get the answer. They don't want to teach you the mathematics. So we're going to learn the details. If you've never done a vector in your life, a month from now it won't make any difference. If you've done vectors a lot, things should be a little easier because of familiarity. That's it. So what is a vector? You have a kid, brother or sister, and they're in, I don't know, 9th, 10th grade, maybe they're in trigonometry or something, and their teacher just talked about vectors today, and they come to you and say, what the heck is a vector? What kind of language are you going to use? By the way, there's no wrong answer, but how would you explain a vector to somebody who's just learning for the first time?
A magnitude and a direction.
Okay, but what is it though? It's something with magnitude and direction, but what does that mean? I mean, is it a circle? Is it a shape? That's a tricky one. I mean, you guys all, I know what vectors are, but if I was trying to describe a vector, now, I want to go over a couple things, basic geometry, very basic geometry, because notation is huge. In mathematics, if I say something but my notation is bad, you might interpret it as something else, something that had similar notation. Okay. What is this called?
Segment.
A line segment, good. Segment means it's a finite piece of a line.
Right.
Array. Ray is tricky. That's infinite, isn't it? But it has a starting point. And then what's the third one? That's just a plain old line. Okay, do we all agree? The notation we traditionally use for this one was we write AB with a little bar over it. This guy, AB with a little ray over it, and this guy, AB with a picture of a line over it. That's the universal notation that you guys hopefully grew up with as kids, okay? No ambiguity here, it's a line segment. There's only one measurable thing in a line segment, it's length, it's magnitude. How long is it from here to here? That's it. This is infinite in length, but I need a couple places to tell me where it is. We know this from baby geometry. If I give you 2 points, I'm holding one between my fingertips. Exactly how many lines can I draw through these? 1. Okay, that's very, very important axiom from geometry. There's only one line. Now, I'm thinking of a line. Do you know what line I'm thinking of? No, the line that passes through these 2 points. Now you know what line I'm talking about. That's why you actually have to have 2 points to describe it. Now the line segment, does it matter whether I said AB or BA? Is it a different line segment if I say BA? Is it a different line if I say BA? Is it a different ray if I say BA? Yeah, because in the ray, the first one is the terminal point. It's the vertex, if you will. Now, the only one that seems a little bit confusing is this one. Because when we talk about a vector, okay, I'm going to do two-dimensional for right now because I can draw pictures of two-dimensional. A vector, first of all, always starts, in its orientation, we always start it at the origin, and then we give it a terminal point. The terminal point, let's say, is A comma B. That's just a point on the xy plane. So how do we represent the vector itself? Let's call this vector V. And the notation we use is this. We have to distinguish between the two. The ordered pair AB is called the terminal point of the vector. It is a very important point. It tells me where the vector stops. The notation, it indicates I'm talking about the physical object as opposed to just the endpoint. The endpoint and the physical object are not the same thing. Okay? The physical object has direction and, as he said before, magnitude or length. So we use different notation, but if I just wrote the letter V, how do you know I'm not talking about a variable or something else? So the vector notation most of you are familiar with is we put a little hat on it. So why is the notation for ray sometimes confusing? Kind of obvious, isn't it? Kind of looks a lot like the notation we use for a vector. We don't put an arrow over a vector, ever. No, an arrow always means ray. Well, what's the difference? A ray is infinite, a vector is finite. That is not the same thing. And that's an extreme difference. This is finite, so the little hat. Now, when you're writing a vector, you put the hat. When you're printing the vector, so if I brought up my first quiz, I've already closed that, but if I brought up the first quiz, I don't use the hat. What a textbook will use is bold notation. Now, I want to make sure you guys understand that. So when you're reading your textbook and you see a bold V, that means it's a vector. And I like the bold because it stands out. There's no interpretation, it stands out. But if I use bold print here, that means every time I draw a vector, I've got to go like this, I mean, really fill it in. That's kind of sloppy. So I just use the hat. So when you're writing it, you use the hat. When you're printing it, you make it bold. That's it. Those are the only two ways we generally ever indicate vectors. But we do want to make sure we indicate vectors versus points. Because there's sometimes we're going to be talking about points. I have points in space that I'm trying to find things about. So that notation is actually pretty simple. There's really nothing complicated about that. Okay, so right off the bat, let's say this is vector V, and that's A comma B. And let's have another vector. Try this. We'll call this vector U, and let's say that's C comma D. Okay? I have two vectors here. There's only two defined operations for vectors. It's kind of boring. Only two defined operations. You can add them, you can multiply them by a scalar, which basically will lengthen them or shorten them. Okay? So I want to add u plus v. Or b, actually, I'll say b plus u. We are going to define vector addition. It's not assumed that you know it, we're going to define it. The symbol, 3 bars. There's a lot of notation that people are really loose with in math in general, and it drives me crazy because I'm a math person, and I've been an editor and a reviewer of more textbooks than I can count, and things they like me to look at, hey, are we using good notation? If the notation I was using was ambiguous, if 2 educated people could possibly interpret something 2 different ways, then we have a problem, don't we? So there has to be an absolute, 3 vertical bars in a mathematical sense always means is defined as. That's infinitely more powerful than an equal sign. An equal sign means it's a result. Is defined as is way bigger. I'm going to give you 2 examples where you have used this, but you may not have realized you've used this. And we use this periodically in mathematics, all right? I have a unit circle here. I know what you're thinking. Wow, blue looks so good. All right. It's a unit circle. Can you calculate the cosine of theta? It's a trick question. Can you calculate the cosine of theta? No. Cosine of theta is defined to be what? X. What is the sine theta defined to be? What is the tangent of theta defined to be? Y over x. Oh, by the way, which just happens to equal sine theta over cos theta, doesn't it? This is the definition of the cosine. It can't be calculated. Cosine is defined to be the x-coordinate on the unit circle. That's it. You can't calculate the cosine. You have to define it first. Oh, now once I define it, I can do calculations. The sine of theta is defined to be the y-coordinate, and the tangent of theta is defined to be that ratio, which just so happens to equal this. This is a result of the definition. Does that make sense? That hopefully you all learned this. Now, having said that, y over x, wait a minute, what else is y over x in this picture? Wouldn't y over x be my slope? So the tangent of theta is equal to the slope of the line. That's why we use the term tangent line in mathematics, because the tangent of the angle is equal to the slope of the tangent line. It's not a coincidence. That's where the term comes from. Now, the square root of -1, can you calculate that? Now, we don't do complex numbers in this class, just so you know. The only part of the 3 semesters of calculus where you ever did complex numbers was in the hyperbolic functions in Calc 1, and you may have had a class where they skipped all of that anyway, so you learned it incorrectly. That's unfortunate, because when you get to 255, you gotta know the complex inside and out. And it's usually not reviewed, it's just thrown at you. That's a tough one. But we don't do any complex numbers in here. We do what is called real valued calculus. Real valued calculus means all inputs are real, and at the same time, all outputs are real. Now, is that restrictive in general? Yeah. Yeah, you're going to find later on there's actually no such thing as a restriction. There are no areas in mathematics that are restricted. The problem is we cannot master the calculus of complex numbers before we master the calculus of real numbers. So all of you who are engineers, probably in about a year, maybe 3 semesters, you're going to take complex calculus. It's called complex analysis. And that'll be one of your first upper division courses. You go to San Diego State, you probably take that next year. Yeah, it's terrifying. That's where, I took that class with Chuck Norris years ago. That's where he learned to divide by 0. Dividing by 0 is just a parlor trick. Yeah, you do it all the time in the complex realm. It's not even a big deal. Can't do it in the real world. Not at all. And it's not equal to infinity. It's not even like that. Yeah. So what is this? You can't calculate it. It's what? It's defined to be I. It cannot be calculated. That's the definition. So the square root of -4 is equal to the square root of 4 times the square root of -1 because of rules of square roots. And that's equal to 2i. I can calculate this based on this definition. So does that make sense? when you had high school geometry, way back when, you learned things, theorems. What's a theorem? A theorem is an absolute truth that we can prove. A corollary is just a weaker theorem, and a lemma is just a weak corollary. So they're still theorems. What is an axiom or postulate? You use those are kind of interchangeable. I don't really put much of a distinction on them. Do you remember those terms, axioms and postulates? Because we use those all the time in math. When I said 2 points, you said there's only one line that can be drawn through it. Can you prove that? Can you prove that? Actually, you can't. You can't prove it. It's impossible. It's a starting point. So the starting point in most areas of mathematics involve axioms and postulates and definitions. And once we have those, then we can build upon those. And when I prove something using those, that's what the theorem is. So when you hear something called a theorem, that means absolutely it can be proved, and it has been proved. And hopefully you even understand the proof. But an axiom or a postulate is a basic starting point that is so basic it cannot be proved. Okay? Now, the simplest analogy I can give to that one is color. All right? So I said, Kenny, can you define the color red? Well, Kenny says, I'm wearing red. So we all agree that's red. What if you're colorblind? No, that'd be a problem. Can you define red? No. Can you define blue? Yeah, I think you're wearing blue. I'm not that good, by the way. Nobody, we know it's blue. Is anybody wearing yellow? You're happy face. Okay, so you saw a happy face. Can you define yellow? No, you can't. This is going nowhere. Can you define green? Actually, you can't. What's green? Blue mixed with yellow. Oh, in fact, you can define every color there is except blue, red, and yellow. They cannot be defined. They are the starting points. They are the axioms. Did you know that? They're called the primary colors. I had to learn this when my kids were little. The primary colors cannot be defined, but every other color that exists can be defined as some combination of the primary colors. They are the starting points. They are also referred to as undefinable terms. Now I'm going to get one more example because we use this all the time in calculus and we use geometry all the time. I taught high school geometry for several years. Okay, and we limit ourselves to 3D in high school geometry. We don't need to go into higher dimensions. We will refer to it, but we won't spend time on it. We actually will do things in fourth dimension, but don't worry about it. You don't have to draw a picture. There are 4 undefinable terms. 4 undefinable terms in geometry. That does not mean they are so complicated they can't be defined. That means they are so basic they cannot be defined in simpler terms. Anybody want to guess what the third one is? It's the final frontier. Space. 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional. Every single word that exists in geometry comes from one of those. So let's take something as simple as an angle. Everybody knows what an angle is. And so how do we usually represent an angle? Something like that. An angle is 2 what? Not lines. Rays that share a common endpoint. But a ray is a directed piece of a line and it has an endpoint. In other words, you can't get angle without using lines and points, can you? In fact, every single thing that exists in geometry ultimately is broken down to that. You have to have a starting point. Now, once I know what something is, I can use that to describe the bigger thing. Once I have a theorem, I can use that theorem, right, to prove a bigger theorem. We do that all the time in Calc 1. That's not even a big deal. I want to define vector addition now. Vector addition is defined to be simply A plus C, in my picture, B plus D. Vector addition is defined to be you add the corresponding components, which right off the bat means vector addition is only defined if the vectors are in the same dimension. These vectors are both in 2 dimensions, so we say it like this. V and U are elements of R2. Whenever you see a script R, that generally means the real number system, because we sometimes will use an R for other things. If we just used a capital R in this class, it usually stands for the region in the XY plane, something simple. The script R we usually reserve to represent the real numbers. So what is R2? It's technically the Cartesian product of R and R. Has anyone here had discrete mathematics? Math 245? You haven't? Do you remember doing Cartesian products? Yeah, Cartesian product just means I take all the elements in one set and I match them with the elements in the other set to make ordered pairs. So if I take all of the real numbers and I match it with all of the real numbers, what will I get? The entire XY plane. Then what if I do the real numbers matched with all the real numbers matched with all the real numbers again? I'll get all of 3D. That's called R3. Oh. So in linear algebra, we study Rn. We study n-dimensional mathematics. And we don't worry about trying to draw a picture of it. And we use vectors pretty much. So this is the definition. Now, stare at that definition for a moment. A, B, C, and D are real numbers, aren't they? And what do I know about real number addition? Isn't it commutative? So wouldn't this be equal to C plus A, D plus B automatically because real number addition is commutative? Well, why is that a big deal? Because then this would be equal to U plus V. We've just proved that V plus U equals U plus V, meaning vector addition is commutative. Ooh. Now, commutativity is not an automatic thing. A lot of people think everything is commutative. All operations I perform are commutative. Addition is commutative. Multiplication is commutative of real numbers. How many here have ever worked with matrices? Okay, is matrix multiplication commutative? No, period, it's not. In fact, it's not even defined in both directions usually. No. Is division commutative? A divided by B is B divided by A? No. Exponentiation, A to the B power, B to the A power? No. In fact, outside of addition and multiplication, there's almost nothing mathematically that's commutative. No, commutativity is one of the hardest things to achieve. It's not an automatic, it's far from an automatic thing. When we're going to do dot and cross product next day, we're going to see cross product, which is the really important vector property we learned for this class, is not commutative. You know, most things mathematically are not, but vector addition is. Yes. And that would be true in all dimensions because all I'm doing is commuting the real number addition. So that's a nice thing. So first rule of vector addition is you can only add vectors that are in the same dimension. And then when you do, you just simply add the components. That's pretty easy. The second operation is called scalar multiplication. Oh, and by the way, when I add these, what do I actually get? What physical object do I get? Well, it'd be as if I took this guy and I added it to the end of this guy, or I took this guy and added it to the end of this guy. They're going to end in the same place, aren't they? Because that shape that I've just formed is simply a parallelogram. Oh, yeah, because this piece is here or this piece is here, and this is my result. That's why it didn't matter what order I added. I'm still going to get to the same place. Now, scalar multiplication. For any real number k, I'll use that v right there. K times v is simply ka, kb. Scalar multiplication is defined by you just take that scalar and you multiply each component by that scalar. Well, that makes things easy. That makes things really easy. Now, there are 11 properties of algebra that apply to real numbers. Those in linear algebra, you're really familiar with this kind of stuff because you do it all the time with vectors and matrices and integrable functions and polynomials of a particular degree or less. You do a lot of stuff. But in general, what are the 11 properties of algebra? Well, you have closure, commutativity, associativity, identity, inverse. Okay, those are the 5 properties of addition. Those are the 5 properties of multiplication. What would the 11th one be? Distributive property. That's the one where we combine both. In algebra, there are 11 things. They're kind of like the 11 things you can do to solve an algebra problem that are legal. I can do all these things. How many of those properties apply to vectors? That's a really important question because not everything necessarily will. So we want to go over that because we're going to do a lot of algebra of vectors in this course. And we want to make sure that what we're doing is technically valid. So I used the term closure. All right, I'm talking to the nonlinear algebra folk. Closure is the single most important property to be satisfied. In simple English, closure means if I take two elements of any set and I combine them using whatever operation you're referring to. Could be addition, could be multiplication, could be anything, could be integration, whatever that you want to do. I have two elements of a set and I combine them using whatever operation we're discussing. If the result is guaranteed to always still be in that set, then we say that set is closed to that operation, okay? In the real numbers, if I was talking about real number addition, let's discuss closure, okay? Now, what are the real number sets? Well, the lowest set is called the natural numbers. The natural numbers are often referred to as the counting numbers, 1, 2, 3, 4, 5. If I throw in the 0, then what do I have? The whole numbers. If I consider the positive and the negative whole numbers, those are called, anybody? Not yet. The integers. Now, up until now, you've always used the same symbol. You always used a capital I. Not anymore. Use capital Z. Now, I wasn't there when the World Math Council made this decision that we'll always use a capital Z to represent integers and then a small z to represent a particular integer, when we always used I. So it's kind of like the secret handshake. So when I'm looking at your work and I see you used a Z, I say, ah, she knows. You know, you're there. When I see you use a capital I, oh, okay, she's not quite there yet. Okay. Yeah, I don't know why, but every textbook from now on will use a Z for integers. Again, I wasn't there when they decided. I was probably in the bathroom or something. But we use a Z for integers. That's the positive and negative whole numbers. If we consider every conceivable quotient of integers, what's another name for every conceivable quotient for integers? Not yet. In other words, every conceivable fraction, those are called the rational numbers. And we use Q for quotient. A rational number is any number that can be written as a fraction. By the way, a lot of people have a misconception about fractions. Oh, heck, I could probably leave that there. I have A over B. I have 3 over root 5. I have 2 over 3. All three of these are quotients, agreed? Are all three of them fractions? Are any of them fractions? Which one? The third one. A quotient is not a fraction. Only the quotient of integers is a fraction. And a lot of people make that mistake, and therefore they can get incorrect conclusions. No, the definition of a fraction is any number that's the quotient of two integers. Now, a rational number is any number that can be written as a fraction. So if I said 1 over 2, 2 over 4, 3 over 6, do you agree those are all the same? They're all equal, but they're all fractions. Is the number 5 a rational number then? I didn't write it as a quotient, but could I? How? 5 over 1, 10 over 2, 15 over 3. Oh, so every natural number is in this set. Every whole number is in this set. Every integer is in this set. These containment goes this way. Now, the definition of a rational number is any number that can be written as a fraction, but there's also a decimal version of the definition that you have to know. If any of you have ever been tutors or you're planning on becoming a tutor, this is really important because it has to do with the definitions in the language. Every fraction either has a terminating decimal or an infinite repeating, which we often just do something like this. Every fraction either has a terminating decimal, and by the way, if I gave you the terminating decimal, converting it back to a fraction is pretty darn easy. If I gave you the repeating decimal, you can use a geometric series from top 2 and convert it back. That means that all numbers have either an infinite decimal representation or a finite. Okay. But there's one more case. Infinite not repeating. That's the definition of the irrational numbers. Pi, square root of 2, right? Things of that nature. E. Very important number, but you cannot represent it as a decimal because you could never stop, it doesn't terminate, and there's no pattern. Oh, That's why irrational numbers can be harder to work with. The best you can do is just to round it off, give an approximation. So if this is every decimal that's either terminating or infinite repeating, then this is every decimal that's infinite non-repeating, and this set is much bigger than this set, by the way. And if we put the two together, then they finally form the real numbers. If I want the complex numbers, I'll keep going, but I don't want the complex numbers today. Now, are every one of these sets closed to addition? I'm not going to prove it. Some of these are axioms. In a discrete math class, some of these we accept. For example, if I add two natural numbers together, am I always going to get back a natural number? 3 plus 5, 7 plus, yeah, because I'm only adding numbers that produce other similar numbers. If I add any two whole numbers, any two integers, if I add two rationals, do I get back a rational? That's one of the first proofs you learn how to write in discrete math. It's actually really cool. I take a over b, where a and b are integers, plus c over d, where c and d are integers, and I prove I get a rational number back again. Oh, awesome. So if I take any two irrational numbers and I add them together, root 5 plus pi, or, negative root 2 plus root 2 is what?
0?
0, which is rational. Oh. So even though there are an infinite number of pairs of irrationals that add to another irrational, I just found a pair that added to a rational number. What does that mean? This says not closed to addition. Ooh. Is that huge? Yes, that's actually astronomical in a mathematical sense. If I take two reals, will I get back a real when I add them? Yeah. When I do two complexes and imaginaries, that gets a little bit wonky. We say, oh my goodness. Now, what about multiplication? If I multiply these, do I get one back? Yeah. If I multiply these, do I get one back? If I multiply, yeah. If every one of these, if I multiply two from the same set, I'm clearly going to get back a number from that set. If I take any two fractions and I multiply them, I get back a fraction. So of course, if I take any two irrationals and I multiply them together, oops, what's this? Irrationals are not close to multiplication. And irrationals are a way bigger set than rationals. Is closure to addition and multiplication automatic? No, these are the only sets that are closed. If you took any finite set of numbers, I wanted you to consider the set of numbers, 1, 2, 3. It's a finite set of numbers. Is this set closed to addition? Well, 1 plus 1 is 1, 1 plus 2 is 3, but 2 plus 2, 2 plus 3, 3 plus 3, those aren't in my set, are they? So this set is not closed to addition. Same thing if I multiply them. I'm going to get back things outside. Oh my goodness. Turns out, there is only one set of numbers, one finite set of numbers that are closed to addition. It's not a very exciting set. Anybody want to guess what the set is? What do you think?
0, 1, 2.
Less. Just 0. Problem is 1 plus 2 is 3. Yeah, the set that includes only the number 0 is the only finite set of numbers that's closed to addition. Wow, that's boring. There are two sets, no, actually 3, that are closed to multiplication. The set that's only 0, the set that's only 1, or the set that's 0 and 1. In other words, closure is not an easy thing to satisfy. That's why I'm going over this. In vector addition, if I add two vectors from the same set, I will always get back a vector of that same set. In other words, in R2, still in R2. If I multiply a vector by a scalar, I get back a vector in the same dimension. You can't change dimension of a vector by doing simple operations to it. That's a huge thing. Meaning I can't work with a vector in 2 dimensions and a vector in 3 dimensions simultaneously. There's no way to do that. There's no mathematics for that. Well, that's kind of a nice thing. Now, another thing about vectors behave a lot like real numbers. So we just proved that we know that vector addition is closed. We know vector addition is commutative. Turns out vector addition is also associative, and with scalar multiplication, it's also distributive. But there's a huge thing there, identity and inverse. Now, identity and inverse mathematically usually go hand in hand, okay? An identity is anything that leaves something unchanged. An inverse is anything that undoes something. So if I said, I'm going to go around and hand everybody $10. Kenny is my inverse. See, Kenny goes around and he takes $10 from every person. Now, Kenny and I both visited you. What's your end result? exactly the same as you started. That means when we both visited you, even though an operation took place, your end result didn't change. That's called an identity. So if I add 0 to a quantity, that's 0 is the additive identity. If I multiply a quantity by 1, that's called the multiplicative identity because it didn't change things. But what if I multiply something by 10, but then follow multiplying it by 1/10? Those are inverses, right? Oh, so I start by integrating something and then I differentiate that thing when I get back to the starting point, because those are inverses. An inverse is anything that undoes. An identity is anything that leaves something unchanged. Is there a vector? Now some of this is common sense, not all of it. Okay, in vector V, I called it AB. Is there a vector out there, let's just call it vector X, for lack of a better name. Okay? Now let's say that's AB plus X1, X2. Okay? I know this is going to give me A plus X1, B plus X2. Okay, great. But I really want this to simply be AB. Is there a vector I can add to vector V, a physical vector, that leaves it completely unchanged? Is that even possible? That I just added this vector and it ended up being the same vector? How could that be? If those are
0, 0.
zeros. Oh. So if vector X is actually a vector of zeros, we have a very clever name for this guy. Anybody know what we call this guy?
The 0 vector.
The zero vector. It's a cool name. And what we usually do is we just go like this. 0 with a hat. Never confuse the scalar 0 with the vector 0. They're not from the same universe. No, no. A scalar and a vector are quite different animals. Now, one of the problems we have mathematically is we're sometimes working in 2 dimensions, we're sometimes working in 3 dimensions, and in linear we're sometimes working in multiple dimensions, different things. If I said the 0 vector, do you automatically know what dimension I'm in? Well, if everything we were doing is in 2 dimensions, there's no ambiguity. But what if we're doing some things in 2 dimensions and other things in 3, and we're all over the map? Then what a lot of textbooks do, which I like, put a little subscript. The 0 vector in 2 dimensions. Because what if it was the 0 vector in 10 dimensions? You don't want to write, 10 zeros. Yeah, it takes forever. So you just write a little subscript. That's an easy way around it, okay? I don't need you to do this because it's never going to be the case where we're mixing dimensions. In linear algebra, you do it all the time. When you get to linear transformations, anytime you're dealing with a non-square matrix, you're going to have 0 vectors from 2 different dimensions automatically. And then you really need to say which one you're in. That's not going to be a thing in this class ever. But this is sometimes you'll see this kind of notation. So anytime I add the 0 vector, so therefore, next question. I want to add 2 vectors, v and x, in such a way that I get the 0 vector. Whenever you combine 2 things and do we all agree the 0 vector is the additive identity of vectors then? Because if I add it to another vector, it leaves it unchanged. I want to add a vector to vector v that gives me the 0 vector. Huh. How can I do that? Only if x is what?
Minus A, minus B.
Negative a, negative b? Could I also write that as -1 times ab? Which would mean I want -1 times v. Or you just say negative v. Oh, that would be my additive inverse. Every vector has an additive inverse. It would be the vector of opposite signs. Great. 0 vectors are very practical. Additive inverses are very practical because we use these to solve algebraic problems at some point. Fairly simple stuff. So now I've got vector addition is closed. It's associative, it's commutative, there's an additive identity, there's an additive inverse, and I can even distribute. Oh, they act a lot like real numbers. And that's always a good thing because If something acts like a real number, then conclusions I make about real numbers I may be able to make about the vectors. Now, next thing. We used the term magnitude earlier. I used AB, okay? Anytime you have a vector, there's an obvious right triangle associated with that vector. I want to find the length of this vector. Now, magnitude is kind of a tricky term. The term magnitude, most people automatically assume it means length. Excuse me, the length is part of the magnitude, but technically magnitude has units. So if we were in a physics class and all my vectors represented forces, which by the way, that's usually what the vectors are going to represent in physics. Hint, hint, in this class, that's pretty much always what the vectors are going to represent as well. So if I said the magnitude of my vector, you wouldn't say my vector is 10 centimeters. You'd say the magnitude is 10 newtons or 10 pounds. In other words, if it's a force vector, the unit would not be length, it would be force. Ooh, so that's a common mistake people make. So when we use the term magnitude, we start with the length, but there may be units associated. For what we're doing now, don't worry about the force part. That will come up more at the end of the course. We will be concerned with the units. Right now, I'd just like to know how long this is. Okay? So one of the things about mathematics that the physics people hate is that we do unitless problems all the time, don't we? Every time you did stuff, baby algebra, you drew a graph in the xy plane, you did things, you found slope. And you said, and the slope of my line is 2/3. You do realize that's an impossible answer to any question. Slope is the change in y over the change in x, which means there always are units for slope. It's whatever the y units were divided by whatever the x units. In other words, slope is a rate of change by definition. So there's no such thing as a slope that is unitless. But we did our whole lives with just finding the slope because we were interested in the numerical values. In the physics class, I said, no, you got to throw in the units. Oh, okay, so if y is, let's say, distance and x is time, then my slope is distance per time or speed. Like, duh. If you've been in physics, you go, oh, yeah, everybody knows that. But we don't think of that in the math sense. So for now, we're not interested in the units. We're interested in the numbers. I would like to know how long this vector is. So the notation we use for magnitude is we use the double bar. Does anybody know the slang term for the double bar? Because you used it in Calc 1 when you did your fundamental theorem of calculus. The Riemann sum, the limit as something went to 0. It was called the norm of the partition. Norm. Norm means magnitude, but norm is maybe a better term sometimes. In Calc 1, the norm of the partition referred to the largest delta x. But we're going to do things where we're going to do double integrals later and eventually triple integrals. So our norm will not necessarily be a length. Our norm might be an area. The largest rectangle has area going to 0. Or the norm might be a little rectangular prism. So the magnitude will be the volume going to 0. So norm is a very general term that says whatever it is you're measuring, could be one-dimensional, could be two-dimensional, or it could be three-dimensional. So we like this term. So if I said, what's the norm of the vector? That's the same as saying, what's the magnitude? And that's, how long is this? Well, that's simply Pythagorean theorem. That would just be this. That's easy, isn't it? See, there's nothing about that I find challenging. So why do I care? Well, if I said, let's keep it simple. I need you to go that way. By the way, how far is that way? Anybody? From where you are, I want you to go that way. Anybody want to get, how far is that way? Infinite, isn't it? You're just going to keep going. Oh, I want you to go that way 100 feet. Okay, what did you say a vector was? You said magnitude and direction. We always describe a vector as magnitude and direction. Now, there's two ways to describe the vector. One is the notation. That means I physically have an xy or an xyz. And I can orient it from there. But when you go outside, you're gonna find this really confusing at times. You're gonna go outside, you're gonna say, where's the XY plane? Where's the Z axis? I can't find it, because there isn't one. So in other words, there's always two ways to describe a vector. One is using notation, vector notation. The other is to actually say, go that way 100 feet. Right? I don't need an XY plane to do that. But how do I, if I give you the direction, how the heck do you figure out 100 feet or 50 feet or 1,000 feet? The easiest way to do it is to take this vector here and first make it of length 1. It's a two-step process. I want the vector in this direction that has length of only 1. So if I had a vector that was of length 10, how do I make it of length 1? I multiply it by 1/10. Oh, will that work? If I had a vector of length 1,000, how do I make it of length 1? Multiply it by 1,000. If I had a vector of length 1/100th, how do I make it of length 1? Multiply it by 100. Oh, I multiply it by the reciprocal of its length. So let's call this little guy U for unit vector. That's the term we use. It's 1 over the magnitude of V times V. And since we've already defined scalar multiplication, this process is quite simple. But a unit vector is an extremely powerful tool. So if I said, okay, I need you to go that way 100 feet, first of all, you take that way and make it of length 1. Now, take that vector and multiply it by 100, and now you have the that way 100 feet. Because I might say 1,000 feet. I always come back to the unit vector, and then I take that and multiply it by the appropriate length. Vectors are always finite. You never deal with an infinite vector. But again, if I said go that way doesn't end, does it? So I kind of need lengths. So let's do a simple example. Okay, let's find the unit vector in the direction of -6, +8. How's that? Keep it simple. I want the unit vector in this direction. Now, this is not a complicated thing, but it does require a little bit of algebra. Okay? So, let's give it a name. Let's call it V, okay? Then I can be lazy and say, now, what's the magnitude of V? Say it's the square of -6 plus the square of 8. And what does that give us?
100.
Well, the square root of 100, right?
Okay.
So that gives us 10. So the unit vector would be 1/10 this. Now, is this a good final answer? I haven't said anything incorrect. Are you happy with this as a final answer? It kind of feels incomplete, doesn't it? I probably should go ahead and multiply. I don't want a number on the outside. So I have -6/10 or -3/5. I have +8/10 or 4/5. This is a better answer. Now, I'm pretty sure I did everything right. I'm pretty sure. It's mathematics. How can you have certainty? Is it possible I messed something up, in other words? I calculated my length incorrectly. Is that possible? Yeah, especially because it's a square root involved. Is it possible that I reduced badly? Is it possible? In a group this big, if I asked you 10 questions each, do you think we'd be 100%? I think with 95% we'd be doing great. But we're going to have some careless errors. How do you know? The square of this plus the square of this has to equal 1. No, that's my check. If it does, then I did it right. If it doesn't, I go back and fix it. But it's kind of silly to say, this is my unit vector, and say, did you check it? Oh, I don't need to. I actually have people tell me, I don't like to check, because whenever I check, I get it wrong. If whenever you check you get it wrong, that means you always get it wrong, period. The check just discovered that it was wrong. I didn't check, therefore it's going to be right. I'm not good with that. So finding a unit vector is trivial. Now there's another simple operation that we do with vectors, and it's a term that we haven't used probably in any other class. It's called a linear combination. The term linear combination simply means I'm taking scalar multiples of vectors and I'm adding them up. Scalar multiples, that's the linear part. I'm not doing things. Now the things, vectors, I can add vectors, I can multiply vectors by a scalar. I can't do anything else. I can't take the sign of a vector. I can't square a vector. I can't take the square root of a vector. I can't find the quotient of vectors. Those operations do not exist. I can add them, I can multiply them by scalars. That's kind of boring. Now, next day we're going to invent operations. That's what dot product and cross product are. There are invented operations that we will show based on their definitions or are internally consistent. But they're not automatic operations. Anybody who's worked with matrices, matrices have exactly two operations also, addition and scalar multiplication. And the addition is only defined if the matrices are the same dimension and in other words, matrices and vectors have a lot of similarities, and so therefore they have a lot of the same rules. So linear combination. I have vector u, let's call it 3, -5. I have vector v, 6, 4, and I want you to find 6u minus 3v. This would be a linear combination. My final answer should be a two-dimensional vector because that part cannot change. Now, it's probably not a great idea to try to do the whole thing in one step in your head because there's arithmetic involved that might make a mistake. So the easiest way to do this, and even though I'll show you the easiest way, most of you won't do it and then you'll end up with the wrong answer and you can't figure out why. What is 6 times u? That would be what? 18 -30 plus, never subtract quantities. Do you know why you never subtract quantities? Because even though you're in count 3, you're still going to forget to distribute the negative sign. How do I know that? Because almost every answer I get when someone writes minus will be the wrong number. The first number will be correct and every number that follows will be incorrect because we forgot to distribute the darn negative sign. No. Multiply the second vector by -3. And then what is it? And now simply add my results. 0, -42. That's it. And there's nothing about the answer that's significantly important, it's just the process. A linear combination means I'm taking scalar multiples of more than one vector and I'm just simply combining them. That's it. Not that exciting, but it's a thing. Okay, we will do stuff like that. Okay, so far so good? So this is pretty complicated stuff, I know, right? We took a square root, we added some things. Now, we've done everything in 2 dimensions so far. I'd kind of like to know how much of this stuff applies to 3. Well, the definition of vector addition is still the same. The definition of scalar multiplication is still the same. Even the 0 vector is still the same. But what about things like a unit vector? Magnitude. How the heck am I supposed to find a magnitude in 3D? That creates a little bit of an issue. So, we're going to figure this out right now. In other words, we need to figure out something that will work. So I'm going to draw a picture of a rectangular prism. Okay. This is not a rectangular prism, it is a picture of one because it's 2-dimensional. All right, let's keep it simple. Let's say that that's A, that's B, that's C. Okay, that's easy enough so far. And what I'd like you to do, let's call that D. Okay, let's pretend this little insert, oh, actually we'll use this. So, see that corner there? I want to find the distance from that corner to that corner back there. I'm in 3 dimensions. How do I do that? So we'll just use the Pythagorean theorem, but the Pythagorean theorem only applies to right triangles, which are 2-dimensional. But we're still going to use the Pythagorean theorem, we just have to be a little more clever. So everyone see what I'm asking here? Is there a right triangle here somewhere? Well, is there a right angle in my picture? Again, you're looking at a picture. This is tricky. There's something called the dihedral angle. Okay? Now, I'm going to go back. If I go to that corner there, and I go to that corner, there's no right angle. But do you agree that the walls, the ceiling, the floor, they're all at right angles? Do you agree with that? So if I took any line running along the ceiling going into that corner, and then took any line running along this wall from that corner, those have to be at right angles because the planes they live on are right angles. Those angles would be called dihedral angles. It's not obvious, but this front face and this back wall are at right angles. Therefore, that has to be a right angle. It'd be like this. If I said, I'm not going to do this because I don't want to get in trouble, but if I took my pen and I ran it across here and then I went that way, it wouldn't even matter what angle I went at it. Those would be at right angles, wouldn't they? How do I know that'd be? Well, hold on. You're telling me if I just line segments, I took a random line segment and then from there went in a different direction for the line segment. How would I measure that? Here, it's my piece of paper. Okay, I'll just tilt my piece of paper now. My line segment coming this way, and I still have a right angle here, don't I? It's actually that simple. It's hard to see it on the picture. But I have perpendicular planes, therefore any line segments that are touching have to be right angles. So I have a right triangle. So what do I have? Well, this side is B. Clearly this one is D. For lack of a better name, how about I call this one, I don't know, E. In my picture, what is true? Tell me the Pythagorean theorem in my picture. Would it be B squared plus E squared equals D squared? D is clearly the hypotenuse, right? When I say the line segment from corner to corner, that's the hypotenuse. What I wanted you to do is, when I go from corner to corner, think of it, go down, and then go across the floor. That's one way to do it. Does that make sense? Oh, or go corner to corner, go along there diagonally, and then go across the floor. And you can clearly see where the right angles are going to be. So, what's E squared, by the way? This would be C. Wouldn't E squared be A squared plus C squared? Oh. Well, no, I'm leaving them in squares right now. Yeah. So rather than the specific, I'm leaving them in squares. You notice something? My 3-dimensional diagonal is the sum of the squares of each of the measurements. This is actually referred to as the 3-dimensional Pythagorean theorem. We've just derived it. There is actually a 3-dimensional Pythagorean theorem. Turns out there's an n-dimensional Pythagorean theorem. So if I was in 4th dimension or 5th dimension, you might not be able to draw a picture, but you could still tell me lengths. So now when the question was, how long is D? D would be the square root of these. That is true. But I wanted to use my Pythagorean theorem. Ah, okay, so why is that important? Because that means I have vector V. Let's now call vector V this. What's the magnitude of vector V? Based on what I just proved. It's actually that simple. Is that a good thing? If nothing else, it's a big whew. So if I had a vector in 4 dimensions or 5 dimensions, the dimensions just refers to how many components it has. Don't try to image a picture. If I have a vector with 8 components, well, what's its magnitude? The sum of the squares of each of them under the square root. That's it. I didn't tell you that, we just figured that out ourselves. And it's simple geometry. So the three-dimensional Pythagorean theorem is how I find magnitudes in 3 dimensions. Oh, okay, there's just one more piece. That's not complicated. That actually is really, really comforting that it's that simple. Now, how can I use this geometrically? Well, let me show you something you already know, and then we're going to expand upon it, because this is really, really useful. All right. A circle of radius r centered at the origin. Do we know the equation of the circle? Anybody want to try?
X squared plus y squared equals 1.
Well, it's not a unit circle, so how about r squared? Okay? If you say, well, how did I come up with that? Think distance formula. If it helps you, oh, what is r, well, what's r squared? Wouldn't it be x minus 0 quantity squared plus y minus, oh, okay, yeah. I can think of this as distance formula. So why am I showing you this? I already know this. Well, oh, same circle, but not centered at the origin. This is the most general case, isn't it? Well, what is the distance formula? Well, it's the difference of these guys squared plus the difference of these guys squared equals the square of this. Because if all else fails, isn't that true, what I just wrote? So a circle not centered at the origin, we know it's x minus h quantity squared plus y minus k quantity squared equals r squared. Then if it is centered at the origin, then the hk is 0, 0. Everybody cool with that? Okay, we already know that. Why would we need to know that? Well, we're never going to deal with circles in this class, are we? Well, hardly ever. Oh, no, no, no. We deal with circles on steroids. See, we deal with way cooler things than that. This is what we deal with. A sphere in 3D. Just so you know, in case you didn't realize, in 3D, the orientation, strangely enough, is X is the one coming out of the board, Y is here, Z is here. This is sort of the universal orientation. So X, Y, Z. So if my floor, if this is the origin, then that's the X-axis, that's the Y-axis, that's the Z-axis. That is the always, in every conceivable case, that's the orientation. So you don't have to, reinvent it each time. Let's call that point X naught, Y naught, Z naught. That's the center of my circle. And let's call the radius, well, we usually don't use R. You guys did a little bit of calculus with polar coordinates at the end of Calc 2, okay? And so, right, X is R cos theta, Y is R sin theta, and all that stuff. We're going to do that in this class as well. But in 3D, we don't use R, okay? Here's my origin in the corner. I have this point right here. I want that line segment right there. Now, if I take this point and I go straight to the floor, that's called a projection. If I project this onto the floor, this is X, Y, Z, I'm going to project it to X, Y, 0 on the floor. Everybody cool with that? Now, on the floor to the corner, that's R. R is the radius of that circle in the XY plane. I can't call this R. It can't be equal. So we use the Greek letter for R. Does anybody know what the Greek letter for R is? You've had stats, would be probably the only place you ever saw it.
Rho?
Rho. And rho, it's almost like a Kirby P. Now, this is not a rule, this is more out of convenience. If we're working in 3D and you see an R, you go, oh, R refers to the radius on the XY plane. But if you see a rho, rho refers to the radius in 3D. So R will always represent the radius of a circle, where rho would represent the radius of a sphere, and those cannot be the same thing. It would be impossible for them to be equal. Okay? And by the way, this is not a rule. This is out of convenience. And so the formulas that we develop later on involving spheres will always use rho, because we're going to have R's and rhos in the same problem at the same time sometimes. So I would like the equation of this sphere. Oh, by the way, this point here is x, y, z. Well, we just used the distance formula over there to generate the equation of the sphere. Could I do the same thing here? Could I use the distance formula in the same way? Yeah. Yeah, and it would be x minus x naught squared, y minus y naught squared, z minus z naught squared equals rho squared. So the equation of the sphere looks a heck of a lot like the equation of the circle, because the equation of the circle absolutely comes directly from Pythagorean theorem. The equation of the sphere comes from the Pythagorean theorem in 3 dimensions. Now again, that's very comforting because that was easy to derive. There was no complication there. You're not going to be going into higher dimensions unless you go into a different area. In mathematics, we often deal with higher dimensions, but that's to prove things, not because it's practical. We don't live in 4 dimensions. Right? It's not very practical to try to do all the math in 4 dimensions, but we need to understand it. A few years ago, I was visiting my daughter who lives in Portland. How many have ever been to Portland? Okay, have you been to Powell's Books? Oh, that's too bad. Powell's Bookstore is world famous. It's probably the biggest bookstore. It's a city block in size. I don't know how many stories, a lot of stories, and I swear it's Hogwarts. Because every time I've been there, I can be looking at a wall of things, and when I turn around, the entire orientation of the place is different. They actually have several checkpoints for parents who got lost. No, not the kids, the parents. And they have a math room. The math section is probably as big as this classroom. And I'll just get lost in there. And a number of years ago, I found a book. It was called YE equals MC squared. And it was written by 2 Cambridge physicists. And it was a very cool book. I learned a lot of things. For example, if I run really fast, I will age slower than the rest of you. And they do a really simple proof. They show if using a pendulum clock on a train, time goes slower. They actually prove that. It's actually a simple proof. It's some cool stuff. But the preface of the book says you do not need to understand mathematics to understand this book. And by the 2nd or 3rd chapter, they're showing the Pythagorean theorem using what's called hyperbolic Pythagorean theorem. That's where instead of the sum of the squares, it's the difference of the squares, which makes it hyperbolic. And to prove the theory of relativity, they use non-Euclidean geometry. You guys know what that means? You've only done Euclidean geometry. Non-Euclidean geometry would be different. Now, think of a sphere, a globe. Think of a globe. If you're, let's say, in the northern hemisphere, and you want to get from one place to another place. So now if I make that globe into a map, a 2-dimensional map, is the line segment the shortest distance between those 2 places? Actually, it can't be. Unless you're on the equator, the line segment would not be the shortest. You'd actually go like this. That's why planes do weird things. Because it's non-Euclidean geometry. The closest distance between 2 points is not a line segment in that. It's curved space, it's weird stuff. Don't worry about it, you're not going to do that unless you do like graduate level geometry. So the book, it says you don't need to understand any math, but everything's done in 4-dimensional non-Euclidean geometry. I've done a lot of math in my life. I barely understood what the heck was going on in this book. It was very cool, but you had to have a PhD in physics, I think, to actually understand it. And they're saying you don't even need to know any math. And immediately they start off with 4-dimensional non-Euclidean geometry using vector calculations, which I just thought was interesting. So I've had students go pick up the book and they say, the first 2 chapters were awesome, and then I was completely lost, started questioning reality. But it's really, really, really interesting. But the fact is they do everything in higher dimensions, which makes it a little bit harder to follow. Okay? But you can prove things in higher dimensions that you can apply directly. I'm going to show you things down the road. Down the road is not that far away, where if we look at things differently, everything you've ever done in your life, you've done in 2 dimensions for the most part, except for maybe some geometry in high school where you might have dealt with 3-dimensional shapes. But I'm going to change the way you looked at things. Rather than look at anything 2-dimensionally, I want you to think of everything as really 3-dimensional, and all you were looking at was a slice. And if you change that orientation of thinking, because we're going to go do some algebra on this in a moment. In calculus, we like doing calculus of functions. We like taking derivatives of functions. What's everybody's most hated derivative in calculus? Not even close. If it's not a function, then the only way you can differentiate it is implicitly. Remember those? Oh yeah, those were a blast. And you probably never did a second derivative because you'd still be working on it. They're so long, they're so complicated. We didn't like implicit differentiation because it was confusing, it was difficult, and so on, because we were dealing with things that were not functions. What if I told you that's no longer a restriction? See, circles are a very important shape. Would you agree? Circles are very important, but they're hard to do calculus on because they're not functions. What if I said, no, we're going to change the way we look at circles forevermore? This is the whole point of this class. What if I'm giving you a little glimpse into the future is all I'm doing. The future's coming up really soon. This is a 3-dimensional shape called a circular paraboloid. It's a cool sounding name. Basically, think of a parabola that just rotated. Okay? I want to take a cross section parallel to the xy plane. Okay? Now, the cross section parallel to the xy plane would be a plane that is horizontal. If the floor is the xy plane, I want to go this many units high. Okay? In 2 dimensions, if I have a vertical or a horizontal line, we know how to describe them, right? X equal a number or Y equal a number. If I have a horizontal plane, it's Z equals a number. Okay? So let's call this plane Z equals K. What am I going to carve out here? I'm going to get this. That slice will produce this circle. Do you agree? It's a circle centered at the origin of radius root k. Okay. I'm going to go out on a limb here and say that every circle that exists is a slice of a circular paraboloid. And a circular paraboloid is a function in 3D, easy to work with, easy to integrate, easy to differentiate, easy to do anything with. And once I make the slice, I move on. Implicit differentiation, I'm going to show you that it will be absolutely trivial. You won't even be challenged by it. When we look at things as everything is 3-dimensional, if you can draw it on a piece of paper, it's a slice of something 3-dimensional. That's an absolute. There's no exception. Anything that's 2-dimensional is a slice of something 3-dimensional. And the 3-dimensional thing will usually be fairly easy to work with. Isn't that cool? You go, I never thought of it that way. Well, but by thinking of it that way, it'll make things a lot easier. We're going to change the way we view a lot of the mathematics because we have to do things in 3 dimensions. We have to have a way of doing things in 3 dimensions. Okay? So, go back to my sphere here. I would like you to tell me find an equation of the sphere with center 6, -8, 3, and radius, I don't know, 10. Okay? Write that down for a second. Let's see if we all get the same thing. Okay, in the first one, I'm giving you the center and the radius, and I'm asking you to find an equation. If I said, I want you to find an equation of a line, most of us would opt for slope-intercept form, right? Y equals 3x plus 5, because it's more useful. But aren't there an infinite number of variations of the same equation? You know, I could double both sides. I could add 10 to both sides. I could move the x to the other side. Manipulating the equation doesn't make it a different line, just a different look. If I give you a parabola, oh, we love it in vertex form, right? Y equals 2 times the quantity x minus 3, right, squared plus 5. I like it in that form, but I could write it in any form and still be the same thing. Right now, I want to write it in the form that looks like this. This is the most useful form because I can read the center and the radius from here. But could I also multiply this out and then gather terms and do all that stuff? Yeah, that's what I'm doing on this one. So the answer to this question would be what? X, what? Minus 6 quantity squared plus
Plus 8.
y minus negative 8, so y plus 8 squared plus,
Minus
and what does it all equal?
100.
Careful, 10 squared, so it all equals 100. Well, that was pretty easy. Now, could you multiply this out? Sure. Should you? Oh, heck no. We'll lose all the information. That's the last thing I want to do is multiply it out. That just makes it more complicated. All right. So, I just need the center and the radius here. Houston, we have a problem. I can't tell you either one. I need to write this one to make it look like this one. You have exactly one tool to do that. Do you remember what it was?
Complete the square.
Complete the square. We learned complete the square in baby algebra as a way of solving quadratic equations. We really use it so we can then derive the quadratic formula. But in general, you didn't use complete the square to solve quadratic equations. You either factored them or just used your quadratic formula. It's more efficient. But you needed them when you had conic sections, because you needed to manipulate and rewrite the conic section. For example, it's how you found the vertex of the parabola, perhaps, or the center of the ellipse, or something like that. So, quick reminder, if I said x minus a quantity squared, that's x squared minus 2ax plus a squared, okay? If that's a plus, then that's a plus. I know this. So if I started with, let's say, x squared minus, well, I don't use those numbers, sorry, different numbers. X squared minus 12x. I want to complete the square. I want to say this equals something. So what you did was you went like this, x minus, now, that coefficient got doubled, didn't it? So when I'm working backwards, what's got to go here? 6. And I always like to do it like this. And then when I go this way, what's going there? 6 squared. So, is x squared minus 12x equal to x squared minus 12x plus 36? Or should I also do minus 36? So x squared minus 12x is equal to x minus 6. Quantity squared minus 36. You with me? Okay, that's quick review of complete the square. So first thing I want to do is rewrite this by putting the similar terms together. And I'm going to throw the 8 on the other side because I really don't need it. Okay? Now, one at a time, let's complete the square. So this is going to be x minus what squared?
3.
3, so what's going to go here? 9. I don't want to subtract 9, because now I have an equation. I didn't have an equation here. So if I added a 9 to the left side of the equation, what would be a really good thing to do? Add 9 to the right side of the equation, because I want to say they're still equal. That makes it way easier. Now, the next one. Y plus what squared? 5. So what goes here? plus 25 plus 25. Okay, and then finally, z minus what squared? 2, and then here we'll go 4, 4. So what have I got on the right side? 17, 42, 46. Now, I've done all the work, but I haven't actually answered the question yet. The question was, what's the center and radius? So the center is what?
-3, -5, 2.
Remember, so it'd be x minus the x coordinate, so 3, -5, positive, so it's y minus -5, and the radius would be, well, I'll use the rub, sorry, 46 squared?
Square root.
Square root of 46, good. Sometimes we go the wrong direction. That wasn't bad, was it? It was just simple algebra. So spheres are something we are going to work with later on in the course, and I don't want them to be intimidating in any way, but all I'm using, everything sphere related is going to be basically three-dimensional Pythagorean theorem. But that's what we did to get this answer. So if I gave you the center and radius, piece of cake. If I ask for the center and radius, that's going to involve a little bit of algebra. Okay, we don't have to do a whole lot more than that. That's probably the most complicated algebra we're going to do. So if you got nothing else from today, right? Add vectors, multiply them by scalars, find a unit vector, do linear combinations of vectors. All of those processes should be very simple because those are the things we're now going to use in the upcoming weeks. Next day's class, there are two major derivations. So one of the things that I'm going to do next day, that I do in this class, I do all the derivations of everything. We do the cross product and all that, and it's necessary that we do all the really nasty math. But I've got all of these things on pre-printed lecture notes. Okay, so some of the stuff next day I'm going to put up on the board, and I'm going to say, just watch. Because if you've ever derived cross product, I mean, that's going to fill up the entire board, and it's like the Matrix movie, you know, all the symbols, and everybody does the same thing, and they take notes, and at the end they're going, I can't read my notes. And then I show you that I did all the stuff already in print, that it's easy to read. So what I'm going to do when we get to some of the stuff, I'm going to put it up there, and you have access to it. You might even want to print those notes before you get here so you can write on them. But that way you don't have to sit there and painstakingly write every detail of everything that I do, because the process is important so you know where things came from, but the conclusion is the main thing. That you understand what the end result is, and it's not just arbitrary. This is calculus, okay? It's not, okay, here's the formulas. Remember when you did derivatives? Someone just gave you like 20 formulas that here's their derivatives, and you said, okay, I'll memorize them. Or you derived them by taking limits and maybe doing other things, so you saw where they came from and saw some were more complicated than others. And then integration kind of the same way. See, I taught business calc a number of years ago. It's not my favorite course. In business calc, they never use the word limit. Oh, limit is evil. So what do they do? Here's the formulas. Memorize them. There's no derivation, so therefore there's no understanding. It's get an answer. But they're not the people that are using calculus like you guys are doing to understand your physics and your higher level classes, your engineering courses. It's all calculus based. So you need to know the why more so than the answer. I need to know why do I do this, therefore I'm going to do the right thing every time. Okay? Everybody cool with that? Any questions? We're going to end shortly. Okay, would you go ahead and press the red button? Hopefully that's still recording.